One, two. We're going to start in a minute. Our speaker is just on the phone at the moment. He's finished. Brilliant. So we're going to start now. So welcome, everyone. Welcome to the Fuse Box. How many of you have not been here before, just out of interest? Okay, so quite a few. So the Fuse Box is an innovation space run by Wired Sussex. And I'm the managing director of Wired Sussex. So for my sins, the Fuse Box was my idea in the first place. And it supports innovators who are interested in taking new and emerging tech and developing really interesting and exciting things with it. So we have a residency program. I think we've got some residents in the audience. Hands up if you're a resident. Yeah, so we've got some residents in the audience. So if you're interested in the residency program and how you get involved in that, then by all means talk to them. We've got some really interesting technologies that we're developing here, which residents and others have access to. So we've got an immersive technology lab where you can create content for VR and AR. And we're currently kitting the space out for 5G. So this will be, I think, the first place in the whole country outside of a university laboratory where businesses can access 5G technology to see what they may want to do with it. And what they may want to do with it, I think, is really important because we believe that the technologies are a means towards an end. And to really make use of those technologies, you've got to bring a level of creativity to play. So you've got to bring some imagination and some inspiration to the party, as well as a kind of tech knowledge. There you go. Oh, we've got an agenda. So this is the agenda. This is where we are. We're at 9:30, so the welcome from me. We're really pleased to have someone help me with the technology. How do I go back? See, it's the technology that lets you down. So Sebastian, we're really pleased to have Sebastian here today to talk about the quantum computing, the quantum computer at the University of Sussex. I did a panel with Sebastian a few months ago, and he was telling me, it's quantum computing is obviously, is it on a timer or something? Rosalie, is it on a timer? He was telling me that the quantum computer that they're building, the large-scale quantum computer that they're building at the University of Sussex, is one of only a handful in the world. So we thought this was a kind of really great opportunity to try and understand quantum computing and try and start to think about what we, as businesses, as artists, as creative technologists, might want to do with that. So I think that's the real opportunity here, to get your head around some of the mind-bending stuff that is quantum computing, to get your head around the scale of what they're doing actually at the University of Sussex, and for us to start to work with the university to think about how we might create what we call use cases, things that the new technology could be used for. So plenty of time for that, plenty of time for networking as well. In the spirit of, can you move on to the next slide? My camera's assistant is going to have to. In the spirit of creativity, we've got a really, just to let you know, we've got a really interesting talk on Monday. We have a writer in residence here at the Fuse Box, Al Robertson, there, who's a science fiction writer. And so he's curating a series of events for us, and one of them is on Monday with a psychogeographer who has done some work in terms of ways to think about real and virtual spaces and written a book on Sussex from a psychogeography point of view. So if you're interested in this and you're interested in other ways to think about the relationship between creativity and technology, by all means come along for that. It's a lunchtime brown bag meeting here.
That's one.
Thank you. Brilliant. And just to let you know about some of the other events that we've got, so I mentioned the brown bag lunch. We run VR Brighton from here, always very, very popular. And the next two VR meetups are in March and April. The one in March is on the music industry, so how is VR and AR disrupting or engaging with the music industry? And they're interesting because not only do we have speakers talking about some of the products and services that they've created in VR, but also there's lots of demos, so there's lots of hands-on stuff. And then the April meetup is around storytelling. So how do you tell stories using immersive technology, and how does that disrupt the traditional linear flow of the way that most media think about stories? Finally, on March 19th, for those interested in blockchain, and particularly getting practical with blockchain, we've got a blockchain app development session for beginners. So if you're interested in developing applications using blockchain technology, then by all means come along to that. That's enough from me and from the technology. I'd like to introduce Sebastian now, who's going to talk about quantum computing, and particularly the work that they're doing at the University of Sussex. Thank you.
But is it going to just cycle through that as well? Do you reckon? So I always have to pause it. Okay, right. This might go weird, this might cycle through as well, so it might go faster than I can talk, but we'll see how that goes. Yeah, thank you for the really kind invite. It's great to be here today. Like I mentioned, I'm going to be talking about quantum computers. I only have about 20 or 30 minutes in this slot to tell you everything about quantum. So I'll do my best. It won't be too technical, lots of nice pictures, just to give you a flavor of what these technologies will hopefully be able to deliver. And I'm also really, really keen to talk to as many of you about how this might help you. This is really meant to be a community effort going forward where we need to come up with new applications, cool applications for these machines that are becoming available slowly. So first off, to kind of introduce the team, these are the guys who are really doing most of the work in the lab. I'm the senior scientist in this group, which is run by Winfried Hensinger, who some of you might have seen in the news before, heard on the news before. So these guys are really doing most of the work, and this is an ever-growing team. The bad news for us and the good news for you guys is that you can buy them already in Worthing. They've done it, we didn't know, so just pop around our shop and get your hands on one of these awesome machines. But joke aside, it would be amazing if we can get to that stage at some point. That's most certainly what we're aiming towards. But yeah, I thought that's quite cool. I wonder if they've actually got that a trademark on that. I don't know. So anyway, let's start with some weirdness, quantum weirdness. So quantum physics is really weird because we don't really observe it. We don't really feel it on a day-to-day basis. And the reason is that quantum physics is a part of physics that describes what happens on the very, very small. So this sort of individual atom, single particle level. As soon as we go to our sort of size, we don't really observe these effects anymore. Nevertheless, they are real, and the sort of things that happens in this quantum world is that, for example, an object can be in two places at the same time. So if I was an atom, I could be over there and over here simultaneously. It's really weird. An atom can also, for example, move forward and backwards at the same time. Or something can go through a solid wall. All really cool, useful things. And then there's also entanglement. which Einstein referred to as spooky, and to be honest, many of these quantum laws, they freaked him out because they are that counterintuitive. But this is actually something where he was wrong for once. This is real. These sort of effects really happen. And what these quantum computers do is they use some of these effects to do things that normal classical computers, for example, can't do. And that's where some of the power comes from. Now, everything I'll be talking about in terms of quantum computing will focus on individual atoms. That's the sort of platform that we're using. You might wonder, what is entanglement? This gets thrown around a lot. So I can give you a very short explanation of that. If, for example, you two had coins, and you both, flip the coins randomly, you would get random results. Sometimes you get heads, sometimes you would get tails. There'd be no link between these coins. It would be random independent results. If these two coins were entangled, every time, let's say, you flip your coin, or both of you flip the coin, and you look at yours, and it says heads, then you would get heads as well. Every time you get tails, you would get tails. Now, it doesn't matter. You can be in the same room. You can be in different planets. They have that link, this entanglement link, that kind of connects them in some really strange way. And this is something that, well, we all find kind of weird, but Einstein called it spooky action at a distance. But that is one of the fundamental things that we use in a quantum computer. One thing I always like to point out is that quantum isn't really new. It's been around us for a very long time. We've made use of it for a very long time. So, for example, the transistor wouldn't work without quantum. So it's already powering our computers that we have around us today. Also, the laser, without quantum physics, it wouldn't exist. The things that changed in the last maybe 10, 20, 30 years is that scientists got very, very good at harnessing these quantum effects and turned them into something really useful. So whereas before we just made use of some quantum effect that happened to have been there, now what we can do, we can control these quantum effects to a really, really good level. So we can decide when something is entangled and when it isn't. We can make something be in two places at the same time whenever we want to. And that really led to a broad range of different technologies, which we call quantum technologies, which ranges from quantum computing, new sensors that are being developed at the moment, which we're actually working on as well, quantum communication devices, and many more. And a lot of these, you might feel that quantum computing is still a little while away, but there are other technologies where you might already be able to buy a quantum device, or it's very close to being marketed. So it's definitely a broad technology to have a look at, on top of quantum computing, of course. Now, you might wonder, why should I care about quantum computers? Why do I need computers? Better computers than we have nowadays. They're great. They do everything I need to do. One thing, and I think that's actually a small point to point out, is that over time, obviously, as we know, computers became more and more powerful and follow this sort of Moore's law, where I think every 18 months, the processor speeds double in speed. So one might argue, well, at some point, that's probably going to break down, and I'm sure lots of you have heard this before, that people do believe this won't go on forever, and we may well be hitting what is possible with current technologies in terms of speeding up these classic computers. So that's most certainly one reason why you might want to think about different technologies that keep on delivering the ever need for faster processors. But to be honest, I think what these computers will do, they won't just keep Moore's law going, they will really provide a completely different sort of scaling. So then, in a nutshell, what quantum computers are, they really form a new type of technology that have very little to do with how conventional computers do, but in a way they will allow you to do certain computations just a lot faster. The other thing to point out is that what we see at the moment, what we think will happen going forward, is that the technology development of quantum computers will follow what classic computers went through 50, 60 years ago. And I'll show you some similarities in a minute. So what can a quantum computer do? And I would say we're really just at the beginning of understanding what these really crazy machines can do. But there are certain problems that right now you wouldn't even trouble a classic computer with because it's too difficult. There are certain problems that would take a classic computer, even the most powerful one we have on this planet at the moment, would take 1 million years to solve that problem. These machines, we hope, will do this in minutes. So this is what I mean. It's not just carrying on with Moore's law. There are certain problems that these machines will just outperform on a massive scale, we believe. So why? How do we do this? So one, we use these weird quantum laws. That's one. And to give you an example of what happens in the quantum computer is, if you look at a classic computer, and we have bits, so a bit can be 0 or 1. So if I have 2 bits, I can represent this particular number here, 0, 1. That one number I can represent with 2 bits. In a quantum computer, we have what we call quantum bits or qubits. And in our computer, for example, if we follow this atom approach, each atom would be a quantum bit. And they can also be 1 or 0. But because they live in this quantum world, they can be 1 and 0 at the same time. And that leads to some really nice effects. So for example, if I then have 2 qubits, I can have 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time. Now, if we then scale this up, very quickly you realize that if I have 100 qubits, I can have that many, I don't even know what that number is, but it's a large, large number, of different numbers simultaneously. And actually, this number roughly corresponds to the number of atoms in the universe. So this is a pretty damn big number. And that's where some of this power comes from being able to be in this superposition. And in general, this is how it scales. It's 2 to the n, where n is the number of qubits that we have in the system. So what can we do? And this is something people always ask us, what can a quantum computer do? What are these super awesome things that you can do? And the first thing I'm going to say right out is that I don't think we've found the killer applications yet. And this is very similar to how classical computers came about. First, people thought they can only break codes, and that's it. And why do we really need classical computers? Because, we're happy. And, we're going through similar things as well, where at first people realized, okay, quantum computers can also be used for code breaking. Similarity there. But over time, we're starting to unravel more and more applications. So in optimization, machine learning, basically people are developing more and more algorithms as we go along. And the sort of application areas that we're looking at and people have identified, I'm not going to read them all out, but in these sort of sectors. If your sector isn't on there, that's really no problem because we are really only at the beginning at the moment. But these machines, generally, the way I'd like to think of it is that because of this superposition, for example, where it can be in multiple states at the same time, the way you can think about it, when you have a problem where the classical computer needs to try lots of different things, like it iteratively goes through an optimization problem, it tries every possible option it has to kind of give you the optimum. Because of this superposition, these machines look at all options simultaneously and kind of try to collapse on the right answer. So it doesn't need to do this one after the other. It's basically like a big parallel computer in many ways. That's how you can maybe think about that and also give you some ideas of what sort of application areas to look at. But at the same time, I don't want to limit your imagination because we really know very little about the application so far, and that is ongoing work. The other thing which I find super cool is that one thing to note is that everything around us can really be described by quantum mechanics. At the fundamental level, it is all quantum. So it makes a lot of sense to use a machine which uses the same laws to understand the world around us, to understand nature, to understand chemical reactions for drug development, and these sort of things, rather than using a machine, a classical computer, which uses the laws of classical physics to brute force try and understand what happens on the quantum world. And classical machines really hate quantum. It's too complicated, they don't like it. So it makes a lot of sense, at least in my mind, to use a machine that uses the same laws to understand that sort of world. And that's what we often refer to as digital quantum simulation or quantum simulation in general, where we basically try to mimic other quantum systems. We basically replicate that in these machines and then play with it in a very controlled way to understand what happens in real life. So, this is really making the point, have we really discovered the most super important application yet? I really don't think so. And to kind of take you through a little bit of a history of the classical computer, allegedly Thomas Watson made this very visionary statement that he believed at the beginning that there's maybe a world market for 5 computers. There are way more computers in this room right now. And that's how we sometimes are limited in terms of what we believe can happen going forward. Also, there's a lovely statement down here. This was in the press where the electronics people said there were too many vacuum tubes and it would never run. The mathematician people said there were no problems complex enough that computers were needed. And for many years, that's what people said about quantum computers as well. It will never work, it is too difficult, it's crazy, and why do I need it? These machines are great. I really have no need for that. And I think we're seeing a similar thinking going on at the moment, and slowly people are starting to realize, one, we can build these machines, and hopefully I can convince you of that in the next couple of minutes. But we also need to really think, what can these machines really do for us, rather than thinking we don't need them anyway. Now, Phil already pointed to this. If we then look at what we had in the 40s, there were maybe 5 computers, maybe 50 programmers, and these numbers take them with a pinch of salt, but there's a low number of quantum computers around in the world right now. So that's maybe surprise number one. They do exist. We do have them, and one of them is at Sussex, and other people around the world have them as well. Small scale, not super powerful yet, but they do work. And we have maybe 50, 100, 200 programmers, not a lot of programmers around. And you can maybe see that the more programmers you have, the more applications you will have. People write apps for a phone. The phone is only useful if it has apps. Our hardware is only useful if we have something to run on them, something useful. So how do you build this thing? Not easy, I can say that, but it can be done. To point out there, at the moment, if you look around the world, what people are really, really excited about, there are two leading platforms that people are using at the moment. And so generally, you can't use anything to build a quantum computer. You need a very good, stable quantum system that allows you to do these operations. Now, superconducting qubits is one, and that's, for example, followed by Google and IBM at the moment, who've made it into the news a lot recently. That is a system where they have to cool their computers right down to near absolute zero, so minus 273 degrees C. Really hard, but works quite well on the scale that they're working at right now. Another really good platform is to use trapped ions, so individually charged atoms, where you don't have to cool this whole computer down to some ridiculous temperatures. They usually work at around room temperature, which is a good thing. I'm going to focus on the individual trapped atoms in this talk, but to be honest, this is also really cool and exciting, and I think these two platforms will go forward, and others as well, for the next few years, and people will see how far they can push that technology, which is perfectly reasonable to do. But trapped ions, why? Why are we following this approach at Sussex and around the world? There are other people as well. One, trapped ions are identical. Now remember, I've said that each atom or each ion is a qubit. It kind of helps if the qubits are the same. For example, the superconducting qubit guys, they microfabricated, they use nanotechnology to fabricate these qubits. That never works perfectly, so each one of their qubits is slightly different. So when you then want to talk to them, if you want to put information in them, that makes it a bit of a pain. Whereas for us, atoms are the same. They're the same in Washington, here in Brighton, wherever you are. They're always the same. That helps. They're well isolated. Now, the one thing about quantum, the reason we don't really observe quantum is because as soon as a system interacts with the environment, it gets destroyed, and it becomes classical. So as soon as I look at an atom, it will be in one place. If I don't look, it will be in multiple places. This is this weird quantum thing. So we have to isolate these systems really well so they do not interact with the environment. That's the reason why they cool the superconducting qubits down to super low temperatures, so everything kind of freezes out. We, on the other hand, we put these atoms in super good vacuum systems where we suck all of the air out so they have nothing to interact with. The other thing we really like ions is because you can control them really, really well. Now this is important. Just like in a classical computer, we have to do these logic gates. We have to process this information in some way. If you're not very good at that, you will get a lot of errors. That's a bad thing. And trapped ions currently hold the world record in how well you can do these logic gates. Don't really have time to talk about that in this particular talk, but we also do error correction. That's really important for us. We can't live without that. And the larger your error rate, the bigger your quantum computer gets. The more error correction we have to do. The way we do error correction is we throw more qubits at the problem. So the better your success rate is, the smaller your machine becomes. And this is why we're quite excited that you can do reasonably good logic gates with trapped ions. We also believe we have a clear route to large-scale devices. And I will talk about that a little bit, especially at Sussex. This is what we're focusing on. We want to build these really, really big machines that can really do something useful for you. But it is technically demanding. I have some more pictures, but these are crazy-looking machines. Not easy at all. So how do we do this with trapped ions? Tom Clancy does a much better job than me at explaining this, so I'm just going to copy his words because they're pretty damn good. So too bad this isn't like quantum computing. You confine ions in webs of magnetic and electric fields. Hit a trapped particle with a burst of laser light to send it into an excited energy state. Then hit it again to ground it. That's your switch. Rows of ions in a quantum logical gate, giving you the smallest, fastest computer on Earth. Neat, clean, perfect. I agree with everything he's saying apart the last sentence. Neat, clean, perfect, definitely not. But everything else is actually pretty accurate. That is roughly how we do that. Now, to show you some videos as well. This is just to show you that you can really trap something or confine something using these webs of electric and magnetic fields. So here you've got an oscillating electric field, and here we're levitating some charged particles in space. And this is what a quantum computer does as well. We apply these oscillating electric fields, but instead of these big dust particles, we trap individual atoms. And these oscillating fields, just in case there are some people who work in this sort of technology area, we use microfabrication techniques, usually based on silicon, where we microfabricate a specific structure that we can apply these oscillating electric fields to, and then our ions, they get trapped or hover roughly 150 micrometers above that surface, and they stay there for days if we do our job well. And then we can move them around, we can input information in them, it then becomes quite nice. So we do a lot of microfabrication as part of building this machine. And this is what they then look like. So each one of these white or blue dots is a single ion, a single charged atom that line up in rows here. Now each one of these becomes a quantum bit, a qubit, that can either be 0 or 1 or both at the same time. So that's kind of what it looks like to us when we actually observe them. So this is some photons that we collect on a camera here that are emitted from these atoms when we shine a laser. Don't worry about the details, but this is roughly what they look like to us. What do these machines look like? I call it an organized mess. That's what I always say. It's not neat, clean, perfect, but they really work. And all of these things, as messy as it looks, they serve their purpose. They have to be that way at the moment. But yeah, so this is actually the quantum computer setup at the University of Sussex. We have a couple more, but this is what you see on the picture here. And you can see, we use classical computers still. We haven't removed them completely, but these machines are then really used to operate this quantum machine. But one thing to point out, so here we're really working with low number of qubits. And if you look around the world, even what Google and IBM, these guys are doing, we're talking tens of qubits, 49, 50, that sort of level that, for example, Google and IBM are at the moment. And we're not really involved in that sort of race. So some people really like to focus on just adding one more qubit. And you can see between Google and IBM, one's got 49, and the next one comes up, well, I've got 50, and the next one, well, I've got 51, this is amazing. The reason we're not super excited about that is that if you think about how large a quantum computer needs to be to really solve most of our problems out there that these machines will be suitable for, you need to be really large. And this will scare you now, but we're talking thousands, if not millions of qubits. This is really the level we need to be at. So even though these 100 qubits can represent the number of atoms in the universe, because of this error correction, because of the reason we have to throw lots of other qubits in to protect our important qubits, we need to be at the sort of millions of qubits. And that's why we don't really care if someone has 49 or 50 or 51. We focus primarily on developing technology that allows us to do exactly that, to scale these machines up to sizes where we can really do some super cool stuff. The good thing is that you don't have to be at the million level to already impact you and be able to do certain problems better than your classical machines. And this is why we have these machines. So this is the sort of low number of qubits, and we will also obviously keep on developing them, where we can already do certain things really well. And this is why we're really excited to talk to you guys and other people out there, to get you guys involved, to think about what these machines can do, because you don't have to wait until you have this million qubit device. That is what we would refer to as a universal quantum computer, where you can run any algorithm that you can come up with on that machine. But if we understand and we know certain applications that you're really excited about, we can already do a lot of cool stuff with smaller number of ions. And that's really the take-home thing. You don't have to wait until you get these massive big machines. You can already do cool stuff right now. At IBM, for example, you can log into a quantum computer there right now. You can go online, dial IBM quantum experience in, and you can program these machines already. They don't outperform a classical computer just yet, and I would maybe say we're 1 or 2 years away from that being the case, but you can already have access to them, you can already program them, so it's definitely the right time to get involved if you think this sort of technology might be useful for you. So how do you build a large-scale quantum computer, which is where we really do a lot of work as well. And we've very recently actually published the world's first blueprint, industrial blueprint, in how to really do that. So because people always said, well, great, you can do 40, 50 qubits. You can never really get to the thousands or the millions. We really sat down and thought very hard about how you would actually do that. And we came up with how you do it, using currently available technology. And this is what we're doing at Sussex right now, that we're actually building this big machine. I've got a picture here roughly, so we're following a modular approach. Everything in many ways has to be modular, where these microfabricated traps, so you can imagine on the surface here, you've got thousands of these qubits just zooming around up here, and then you've got layers of electronics that control these qubits, that input information into these qubits, etc. This is roughly what it looks like. I've got a video later on that actually explains that a bit better. But the reason I put this up is because if you compare this to what our modern processors at the moment look like, then it's actually not that different. You've got layers of transistors, and the transistors in our case are qubits, so I've got them here, and then you've got all these layers of routing and back electronics that control these transistors below. And we have something very similar. So we've got the hard working qubits at the top, which are analogous to your transistors, and then you've got electronics at the back, which all feeds into the top layer to control these. So actually not that different in terms of what we're trying to do here. It's just quite often people forget how complicated it actually looks like if you were to open your processor up. So have a look, we've actually got a video here to show what our architecture really looks like. So these boards that you see popping up now, they are these qubits, these trapped ions, and this is the surface that I talked about, the microfabricated surface, and we can really move these ions around. And what we have, just like in a normal computer, we have processing zones, and ignore some of the details here, but we move this information to processor zones where we do these logic gate operations to put something in a superposition, so in 1, 0 at the same time, or controlled NOT operations. And at some point then we go to the sort of detection zone where we want to read out, we want to get the information out of these systems. We do that in a specific way, we send some lasers in, and we collect these photons. And these photons basically tell us what state, was it 1 or 0 or both at the same time, when we then detect that. And then, when we zoom out, this is basically an error correction protocol we're running here, which will always be on the back end of a quantum computer. We then put more and more of these chips together until we get to a modular size. This is then one module that we've looked at before. And what we then want to do, very naively, is just stack lots of them together. Lots and lots. So we're currently working on setting up this sort of module. And as soon as we're there, then it should get reasonably easy to just plug more and more of these into a frame. A bit of technical detail, but you can imagine just plugging them together isn't super easy. What we want to do is actually physically shoot individual atoms across these modules. For that, you have to align them reasonably well, but this is just to show you can do this. We've done the numbers. This is not outlandishly crazy, what we're planning on doing here. And then you just build this up. Super easy, But this is a bit in the future. But even one module, I guarantee you can do super awesome stuff. Some really, really cool stuff. But this is just to show that this really scales up. And the Daily Mail, they covered this work a little while ago and pointed out that this will be, the size of a football pitch in the end. And that is roughly correct. But that isn't too bad. If you look how big data centers are, they're much bigger. So this isn't actually that big if you compare it to what we currently have with classical computers. But it won't be on your desk anytime soon, that's for sure. But the sort of thing that we have in mind is that they will sit somewhere out of your way, and via the cloud you interact with this technology. Because you wouldn't want to do your word processing on these sort of machines, but there would be certain problems that are just really, really difficult, and you just outsource it to a quantum computer that will sit somewhere via the cloud. That's the sort of thing that we have in mind. So what do we know? It's most certainly possible to build these machines, and that always is still news to people. They are coming. We have small devices in the lab right now. They are starting to really push the classical computers to their limit to still keep up with what our machines can do, and very soon we will outperform them. It is only a matter of time. It is very expensive, very costly, and time-consuming. And to put some time scales on there, so at Sussex, for example, the sort of module thing that I showed you, that should be complete in around 2 years' time. And the super large-scale device, the more money, the quicker it goes, but it isn't cheap, but it's the sort of 10-year plus. But, and this is a big but, you do not have to wait for this thing here, for the large-scale device, for it to be something really useful for you. That's the really important thing. And this is where you can also have an edge over someone else. You know, if you get involved in this and we can work something out that will help your particular application, these computers aren't around that often. You know, other people won't have access to that. And you're the first person to think about something cool these machines can do, might help you a lot. Yeah, and you know, we most certainly already know that they will transform science society, but I think we have a lot more work to do to really understand what else these machines can do on top of what we already know. And the other thing, we also know that we need a lot of people, differently skilled people. This isn't just physicists anymore. In fact, the last couple of people we've employed were engineers, electronic engineers. You've seen like the top layer of our module, for example, yeah, that's quantum, but anything below that is engineering. We need software developers to write these compilers that, for example, translate Python code into these quantum machines, and you don't always want to be thinking about quantum too much. You just want to write your code, you compilers to translate that. Lots and lots of different people need to get involved in this. Business developers, marketing people. It's a completely new technology that's ramping up right now, and we need all sorts of different skills to make that happen. And I then leave you with this particular question. You know, have a think about what these really, really ridiculously fast computers can do, which in many ways operate in parallel universes. There you go. I'll leave that thought with you. Thank you.
So we've got some time for questions, contributions, or responses to this slightly challenging question that Sebastian has thrown to you. So who's first? Yeah.
Can I just ask about the analogy of these machines to classical machines, say sort of 50 years ago? Normally think of something in terms of like memory, processor. Is there when you've done this computation, where is the stuff stored? Would be my question.
Yeah. So one of the
it seems to be like a processing unit, basically.
Yeah. It pretty much is.
Yes.
And especially with this error correction, we can store things for very, very long. Like that is not a problem. The problem is the information that you want to access is limited what you can get out, because as soon as we look at these sort of things, it kind of collapses. So, you know, in this optimization example that I gave, yes, it can look at all the different options, and it kind of computes all the different options, but it only gives you one answer out. And the task of the software developer or the people who develop these algorithms is to make sure that it looks at everything, but by the time you get to the end of the algorithm, you better end up at the answer of what you're interested in. If you're then interested in something slightly different, you're going to have to change your algorithm a little bit, which is slightly different to classical computers where you can just, you know, output me everything that you've kind of done along the way. That doesn't really work here. So and this is why you couldn't just run a normal code that you use on a classical machine on these machines right now. You have to think differently. And this is where, you know, we try to get people involved. There will be quantum software developers, I have no doubt, who can understand the sort of rules that you have to stick to when you write code for these machines to then really give you the answer that you're after. But yeah, we have processing zones where we do these logic gates. We can then park these qubits, which hold that information for however long as you want to. And then at some point, it's got to interact with you, become classical, and give you that limited information out that you're after.
So it's kind of suitable for some problems and not others, where you can break it down, analyze it into little
I would never say that these machines will be able to do everything, and there will be lots of things where you wouldn't trouble this particular machine for, but you would just use a classical computer. You know, you're not going to do word processing or certain things which just work on a classical computer. So I'm pretty convinced of that, although maybe that would be a statement in 50 years where, you know, actually at some point we do use quantum computers for everything. Do you have to have like a
massive array of storage to operate your quantum computer?
On the classical side?
Yeah, on the classical side.
So we need pretty big machines on that side as well, absolutely. Especially when you take the data out to kind of interpret that in the right way. But nothing we don't have currently around.
Okay, thank you.
Hold on.
What some of the biggest barriers to scale?
Yeah, so...
Would you be able to ask that again? Because we are
Yeah, sure.
recording and just so everyone can hear.
Okay, cool. I was just wondering what some of the bigger barriers that you're facing on scaling up are.
Yeah, so the quantumness in many ways. So the fact that we have to protect our quantum system against any environmental change or the environment as a whole is not easy. And the bigger you make this just becomes harder and harder. But it's an engineering challenge. So there's no, we don't have to invent new physics to make these particular things work. We just have to work really hard to protect these quantum systems from the environment. And that is a challenge, and we're working on that. But this is why it takes a bit of time. And this is why we can't just immediately jump to it, because we just have to develop the engineering required for us to do that. But it's an engineering challenge. Either end.
Yeah.
I mean, it strikes me that actually one of the skill sets that you might need is a philosopher as well, because the whole idea of things being in completely different parts of this planet or another planet, but still being influenced by each other, entanglement. Yeah, I genuinely can't get my head around that.
Yeah, that's absolutely right. Yeah.
I've got a question about the software side. So I've been a programmer for a long time and used many different languages, and things have changed a lot. But at the end of the day, it's still, you're dealing with variables and if statements and loops and conditionals and stuff. So to program a computer like this, I mean, does your thinking have to radically change? Or are you still dealing with, for loops and conditionals and variables? Or, I mean, do you need to think differently, completely differently to enter this world?
You have to think a bit differently. I can't tell you exactly how differently you're going to have to think, because we're only just working this out as we go, if you then run these algorithms on these machines. But you have to think a bit differently. But, for example, you can already download, for Python, for example, you can download quantum libraries that kind of can restrict you to the sort of things that you'll be allowed to do. The language that you use is still the same, but certain things just won't give you the result that maybe you were after if you didn't stick to some of those rules. But this is actually something that we're working out right now, and to kind of develop compilers which make it as easy as possible for guys like you, for example, to still stick within the framework that you know so well, and still be able to operate these computers. But we're at the beginning of that.
And a quick follow-up question then would be, I mean, can you recommend any resources to go and look at which would help us understand what are appropriate problems to take to a computer like this, and what are not appropriate?
Go to your imagination, number one, that's for sure. But it's a difficult one, and quite often we just directly work with people, because there's no one book where you can just I read that and all of a sudden I can think of all these applications myself. It's actually a lot of back and forth with the people who understand how these machines work and what the limitations are, and for us to also understand what you would like to do. So I don't think there is a simple one resource out there. I can definitely recommend get your hands on the IBM experience, for example, where you can program these things already and you can play around with that for a bit to get a feeling for what these machines do. And you live program. I mean, you submit your code and they run it, and you get something back to kind of learn a little bit on that. But other than that, I'd really recommend just talking to us to have a dialogue to see what might be possible in your area.
You said early on, and I think we all understand, that quantum effects are pretty weird all over the place. And you've given us some very good explanations of some of them. Early on, you said a qubit can be in any state all at the same time. 0, 1, 1, 0, 0, 0, 1, 1. Do you have a simple explanation as to how you know which state to interrogate? If it can be anything at any time.
So what the state actually is at the end of it?
Yes.
Yeah, so this is probabilistic in the end. So the problem of we can't look at it once and immediately know it was on 1 and 0 at the same time, because it only gives us either 1 or 0 when we look at it. But if you run this multiple times, you will actually find out. So let's say you're on an equal superposition between 1 and 0, so you're in both states simultaneously equally weighted. If you then look at that 100 times, so you repeat that 100 times, you would then get 50-50 between the two. And that's kind of then how we know it was actually in both at the same time. Doing this single shot is in a way possible, but it becomes very complicated because of, it just destroys it as soon as you look at it.
Right, yeah, I'm not a programmer, but I do read a lot of press, and there's been, coming for years, talk of superconductors and the having to be at absolute zero, and I think a lot of guys are trying to work out how to do that at room temperature, and the graphene's been on the horizon for ages. Is that got any part to play in what you're doing here, or is that just a completely different technology?
Well, I think if you can get higher temperature superconductors, that in some way may help, but the problem is still that, and it's not quite the technology that we use, but the problem that the superconducting qubit guys have is that not only do they need to make their material superconducting, but they need to freeze out the environment as well. Because any material, anything around it that moves around a bit, destroys their quantum system. So I'm not sure it would solve their problem as such. It would maybe make it a bit easier, but they still have to freeze out the entire environment around them.
Hi there. Yeah, that was fascinating. Thank you. I'm a science fiction writer, so it's not so much my job to ask how does this work as kind of what's it mean. I'm very curious that as you're working with this, Phil's touched on already that this stuff is philosophically very challenging, that the more you dig into quantum, the more it can send you back into the world kind of going, wow, things don't work the way I thought they did. And as you work with it, building computers, building this stuff, how has that experience been for you guys? Are there sort of new ways of thinking about things beyond the computer itself, new kind of metaphors for understanding the world that you've been forced to think through? Go, oh my God, this is kind of peculiar. What's that experience of working with it all
It's
like?
cool. You kind of get used to it. It's kind of weird, but sometimes you're right. You need to step back and actually and I say this to PhD students as well, do you actually realize what you're doing here? This is phenomenal. It is really weird, but you get used to it. But it never kind of grows old to come into, to run this machine and being able to say, right now there is something in two places at the same time, which is just mind-boggling. And in the evening you maybe have some very interesting thoughts about that. But yeah, it is cool. It is amazing, no doubt. But and it gives you a different perspective on nature, that's for sure. A lot more respect and curiosity as well.
Yeah, how are you managing that side of things? So, for example, when you talk about building a coding language for something like this, I would assume that part of the question it has to answer is not just, how do I write commands to it, but what does it mean to be writing a command to something that can respond to it in several different ways at once? It's not a kind of classical language where there's always one single fixed set of meanings, and you have to be very careful with them. Are you sort of digging into that kind of, philosophical isn't quite the right word, but the practicalities of working in this limited world with a thing that can be unlimited in the way that our perception of this limited world isn't? Is that something you guys
I think about it and I always arrive at the same answer. That's just so annoying. It's a pain in the ass. Because it becomes classical as soon as you work with it, which is annoying. And it limits us in many ways. I mean, it would be amazing if that wasn't the case. But I try not to think about it too much. It's maybe the naive answer to that.
Before, can I just take someone who's... Because I know this side of the room is...
Hi. This might be a bit of a funny question, but are these so big at the moment that are there other environments where this might be easier to do? So like in space, for example, is anyone doing, if it's interacting with charged particles and things like that, is there anything to be said for doing it somewhere else?
We're not doing it at the moment, and you'd have to get a lot of PhD students into space and get them to work with it. No, I mean, quantum technologies are making it into space. So that's most certainly something where, for navigation, so, I mean, atomic clocks, for example, people are trying to put that sort of technology into space, but it's very hands-off in many ways. You build it here, kind of working, make it robust, put it on a rocket and launch it up there. I don't really foresee launching a quantum computer into space to make that easier. If there are better environments, I mean, in many ways, we recreate the space environment using these vacuum systems, for example. So the sort of vacuum levels that we get to, I mean, I said we suck all the air out, we really do. If you were to step outside the ISS, International Space Station, you'd have a lot more air to breathe than in one of these systems. There's nothing in there. It's one of the things we have to work hard on to protect these systems. So in a way, we make ourselves that sort of environment that these systems like.
So I've got a quick question, which is why Sussex? Is it just happenstance? Is it just coincidence? Is it just someone at Sussex had a good idea? Or is there any tradition at the University of Sussex that may have kind of led to it at one of the handful in the whole world being here?
I think, there's obviously always some coincidence involved in that, but one thing Sussex is good at, they let us bend/break the rules a lot, and certain things that we sometimes have to do quickly and get new people in these sort of things. Sussex is really, really good for that. They're super supportive. they really let us get away with a lot. That's for sure. But I mean, one of the things we just have is we were one of the very few people who really asked that painful question of how do you do this on a big scale. You know, it's very tempting, especially for academics, to think, well, I'll just add another qubit and I get another Nature paper out, and this is also great. But a lot of people then shied away from asking that big question. We just sat down and did the math, so to speak, to work out a way and how to do this on a big scale. And that's helping us a lot now, because it's motivating everything that we do on a day-to-day basis, and it's kind of feeding into the technology development that we do. So everyone in the group, whatever they come up with, is always like, well, does that work on the bigger scale as well, or would that only last for a year and then we have to rethink again? And I think that's where we have a bit of uniqueness, and I think that will help us more the further we go on, where some other people who are doing really well right now and they're building some amazing machines, it's going to be the reverse for them, because they're going to have to start thinking from scratch when they really want to scale up massively. So,
I just want to try to clarify in everyone's mind, perhaps, or my mind at least, what the physical mechanical properties of a qubit are at quantum level. So, you hear about wave-particle duality and spin states and things like that. What the actual physical mechanical property that you're looking at
so we use
to get
spin.
your qubit state?
Yeah, so we encode the information in the spin, and the electronic spin. That's the electrons that zoom around the nucleus. We actually just work with the outer electron, and we change the spin of that. So we apply...
there's 6 possible states, are there?
Sorry?
Are there 6 possible states for the spin?
No, I mean, because we take 2 different electronic states that we can have. They are 2 qubit states, and we can be anywhere between that. So we only work with 2 energy levels that are allowed with this particular electron.
Okay, but the actual thing that you're looking at can exhibit lots of other properties which you're not looking at.
Oh yeah, I mean, there's a broad range, and to be honest, we work very hard to only have the properties that we're interested in.
So is there any room for expansion there?
Always. I mean, people add levels to these sort of things. You could imagine not having a qubit, which would be like a 2-level thing. It could be 3 or 4 or 5 levels, but we're still trying to get our head around the 2-level thing, so we're not going to the multi-level. We're trying to make it as simple as possible while maintaining the nice quantumness, so to speak.
All right. So I think Justin Trudeau was famous for explaining quantum computing in a few words, but he was wrong. It's not really the wave-particle duality, which is what he was referring to, but it's the spin state.
Well, I think he goes more fundamental in that sense. But if you ask me the question of what part of the atom in that sense do we actually manipulate and play with and use as our qubit, it is the spin state. But there are some other people who use other features of the atom to build quantum technologies. So it really depends who you talk to and what exactly you want to get out of your atom in this sense.
All right, thank you.
Hi. I'm really interested to know if there's any commercial sponsorship in what you're doing, or is there commercial sponsorship on the horizon?
Yeah.
And secondly, how do you see this being monetized?
Yeah, so good questions. So yes, we do. So industry is already involved in this. We have various industry partners who do fund us and help us bring this along. And it's like a mutual benefit relationship. They learn something about quantum, and for a lot of industry, they are asking the right questions, like what is quantum going to do for us? Is it going to change our business model? Do we need to think completely differently? What if a competitor has this? Are we out of business all of a sudden? So there's a lot of interest, and they fund us through that worry as it is. But it's mutually beneficial. It's really that we give something back in terms of understanding and knowledge, and we get some money to progress with the hardware side. The second question, what was the... how do we monetize this? Okay. So one thing, and that's already starting to happen right now, is that you can imagine that you sell time on a quantum computer. So you guys would be interested in maybe running an algorithm, or you have some application in mind. You now need to get your hands on the hardware. I doubt many people have the deep enough pockets to build this up from scratch. So you're going to go to some of the guys who have that and pay them to let you access that machine to get some money out of it. And that's most certainly the simplest, earliest route to getting money out that we can see. And this can be pretty expensive, given that there aren't many machines out there that can really do some cool stuff for you. and going forward as well. But there may well be more. We're kind of thinking about this, but we're also not experts in that area. But I think the sort of selling time thing makes sense. And just like via the cloud, you already use cloud computing. You do some of your processing on some big, super powerful computers, and you pay AWS or these guys some money for that. So it'd be similar in this case.
Time for one or two more questions. Is there any last questions, or is your brain still melting?
Oh, sorry, can I? Yeah,
Let's someone who hasn't asked one, and then we'll finish with you.
I was wondering, what do you think is the link between quantum computers and artificial general intelligence?
So this is really interesting. I'm really interested about this, especially with machine learning as well, because, and I'm no expert in machine learning, but I think there's something to be said about them two benefiting from each other, I think. And I'm talking more about machine learning right now. I mean, AI is maybe the next step along, but to get these computers working on the bigger scale, I think we need machine learning. And vice versa, I think we can help machine learning a lot, because if you look at the maths of machine learning, manipulating really large vectors and these sort of things on the big data side, that is how quantum mechanics really works. In this sort of quantum world, you think about vectors. All we're doing here when we do algorithms, we just manipulate these quantum vectors. We just have more space. We just have bigger vectors that we can access with these sort of resources. But I think the underlying maths is very similar. And there's already a quantum machine learning field that's emerging right now, which I think is super interesting, because there are a lot of similarities between them. So yes, I think it has a lot to say about that, but we're only just starting to explore that. But I think that the sort of machine learning AI, they will help each other, actually, I think.
Yeah, sorry, I was just wondering, as someone deep in the field, do you have any recommendations of kind of good books or sort of sources of information about quantum computing and the quantum field in general?
So popular science books? Yeah, absolutely. I can give you some. Jim Khalili, for example, writes a lot about this sort of stuff, and really well. He's got 2 books, I think, out on that. John Gribben is also really heavily involved in bringing this out in a much better way than I could ever explain it. So they're the 2 that spring to mind right now. But I can provide some resources as well, absolutely.
So we'll share your reading list with the class afterwards. We'll share it with all of you. I think it's been really fascinating and really kind of interesting, and it's really amazing that something that is potentially so mind-boggling and groundbreaking is on our doorstep. One of the things I think I want to do after this is try and organise a field trip to actually see the computer itself and meet some of these people who are getting involved in it. Please hang around. I'm sure there's more coffee left, and yes, I'm getting the thumbs up for coffee. Croissants? Fun? Maybe. There's a few croissants and a lot of coffee, so get wired for the next half hour or so, and if you want to grab Sebastian and chat to him, I'm sure you can hang around for a while. Sure. But thank you very much for coming. If you want to learn more about some of the other stuff that we're doing here, have a chat to me, or have a chat to Rosalie, or have a chat to some of the residents about what they're doing. So in time-honoured fashion, I guess, we should once again thank Sebastian for coming here this morning and talking to us. Thank you.